The Pacific Ocean doesn't warn you. It doesn't send a signal you can hear or see from shore. It simply rearranges itself across millions of square miles of open water, and within months, the consequences show up in places that have never seen the ocean, in the cracked soil of Indian farmland, in the dry riverbeds of northern China, in the empty grain stores of Brazilian villages. This is the story of what happens when the world's largest ocean shifts, and why the last time it shifted this dramatically, more people died than in the entirety of the First World War. To understand what's happening right now in the Pacific, you need to understand the machine that normally keeps things stable. Picture the equatorial Pacific as a kind of thermal conveyor belt. The trade winds blow steadily westward along the equator, dragging warm surface water with them all the way across the ocean toward Indonesia. As that warm water piles up in the west, cold water rises from the depths off the coast of South America to replace it. The result is a temperature gradient stretching thousands of miles. Deep, warm water in the west, cold upwelling in the east. This gradient organizes weather systems across half the planet. The monsoons of South Asia, the rainfall patterns of East Africa, the hurricane tracks of the Atlantic, all of them are downstream effects of that one arrangement of warm and cold water. When the trade winds weaken, everything unravels. The warm water that was being pushed west starts sliding back eastward. Ocean temperatures in the central and eastern Pacific rise. The cold upwelling off Peru weakens and disappears. Scientists call this El Nino, not a storm, not a disaster in itself, just an oscillation, a rearrangement of heat across the ocean's surface. But that rearrangement doesn't stay in the ocean. A warmer ocean evaporates more intensely. The atmosphere above it absorbs more energy. Pressure systems that had been anchored in place for months begin to shift. The subtropical jet stream dips southward, routing Pacific storms into California and the American Southwest, while pulling rain away from the tropics, and the effects don't stop at the Pacific's edge. They travel through the atmosphere like a slow shock wave, reaching India's monsoon, southern Africa's growing season, Brazil's semi-arid interior, all within months of the event reaching full strength. India's monsoon is the most vivid example of how far this signal carries. Every summer, the Asian continent heats up faster than the Indian Ocean. That temperature contrast draws warm, moist ocean air inland where it rises, cools, and releases months of rainfall. Over 1 billion people have organized their entire food system around what those 4 months of rain produce. When El Nino weakens the temperature contrast that drives the monsoon, the rains stall. A 20% shortfall is a hard year. A 60% shortfall is something else entirely. And the farmer in Gujarat or Tamil Nadu has no way of knowing that the reason his fields are dying is a patch of unusually warm water sitting in the middle of the Pacific Ocean, 10,000 kilometers away. In 1877, they had no way of knowing at all. The trade winds had been weakening since late 1876. A pool of anomalously warm water had been spreading across the central Pacific for months. No instruments existed to measure it systematically. No global monitoring network connected the dots between the thermal shift happening at sea and the dying crops on shore. The farmers who would bear the consequences planted on their normal schedules, expecting the rains that had always come. In the Madras region of southern India, some districts recorded less than 10% of their normal rainfall through June and July of 1877. Temperatures exceeded 110 degrees Fahrenheit. Seedlings died in the ground before they reached knee height. The soil cracked open, the wells dropped, and the monsoon that was supposed to arrive simply never did. What made 1877 catastrophic rather than merely devastating was that the same shift hit multiple continents at once. Northern China saw almost no rain through 1877 and into 1878. The inland provinces that fed hundreds of millions of people watched their harvests fail for 2 consecutive years. Brazil's semi-arid northeast, the Sertão, dried out completely for 3 consecutive growing seasons. Parts of eastern Africa and the Philippines failed on the same timeline. The same ocean warming, the same atmospheric disruption playing out across India, China, Brazil, and Africa within a single compressed window. There was no good year anywhere nearby to borrow from, no surplus region to compensate for the deficit. The mechanism of mass death wasn't simply a failed harvest, it was the cascade that followed. When a farming family loses 60% of what they grew, they consume everything in their storage and still come up short. Local grain reserves were never designed to sustain communities through multi-year failures. Within weeks of the failed harvest, the buffers were gone, and then the market took over in the worst possible way. Merchants and landowners holding grain recognized that scarcity was coming and withheld supply, waiting for prices to climb further. The food that existed concentrated in the hands of those who could pay multiples of the normal price. The drought destroyed the harvest. The market then determined who survived the shortage. The diseases that killed most people were cholera, typhus, and dysentery. These were spread through water sources that drought had concentrated, and through the crowded, undersupplied relief camps that colonial authorities eventually organized. But the real killer beneath the disease was hunger. A person who has been severely undernourished for 2 months doesn't simply feel weak. Their immune system is running at a fraction of its normal capacity. A minor intestinal infection that a healthy person would survive becomes a death sentence for someone whose body has no reserves left to fight it. British colonial medical records estimate that cholera alone killed somewhere between 4 and 6 million people in India during those 18 months. The recorded cause of death was infection. The underlying cause was the Pacific. The total death toll assembled from colonial census records, missionary accounts, grain price records, and tax rolls sits between 50 and 60 million people across roughly 18 months. The uncertainty is honest, and the worst affected regions had no reliable vital registration, and in many districts the people who would have recorded the deaths were among those dying. But the order of magnitude is not in doubt. This event killed 2 to 3 times as many people as the First World War in half the time with no weapons. Some provinces in northern China lost a third of their entire population. Districts in southern India saw registered household counts fall by more than 30%. Agricultural knowledge that had been passed down through generations died with the people who held it. Parts of southern India didn't return to their pre-famine population levels until the early 20th century. The scientific framework that explains what happened in 1877 wasn't assembled until decades later. Gilbert Walker, a British meteorologist posted to India in the early 1900s, discovered that atmospheric pressure in the eastern and western Pacific oscillated in opposite directions on a regular cycle. He called it the Southern Oscillation, but most researchers at the time treated it as a statistical curiosity. The real breakthrough came when Norwegian scientist Jacob Bjerknes recognized that Walker's atmospheric seesaw and the ocean temperature shifts of El Nino were the same system viewed from different angles. The ocean warms, which alters the atmosphere, which weakens the trade winds, which allows the ocean to warm further. A self-reinforcing loop. Once it begins, it amplifies itself, and that's why events that start as modest anomalies can grow into planetary-scale disruptions within months. The 1982 El Nino was the first observed in something approaching real time, and it still caught the scientific community completely off guard. Ocean temperatures along the equatorial Pacific rose more than 7 degrees Fahrenheit above normal. The forecasting models of the era missed it entirely. The institutional response was the Tropical Atmosphere Ocean Array, roughly 70 sensor buoys anchored across the equatorial Pacific, measuring water temperature at multiple depths and transmitting data to satellites every few hours. When the 1997 El Nino arrived, scientists saw it forming months in advance. Governments were warned. And yet, even with that preparation, 5 million people in southern Africa came within range of famine. Indonesia, hit simultaneously by El Nino drought and a currency collapse, saw food prices rise more than 50% within months. What 1997 demonstrated was not that preparation was futile. It was that even a prepared world struggles when a strong event hits multiple major producing regions in the same growing window. This is what makes the current situation in 2026 worth understanding carefully. The global food system is built to absorb shocks, but only isolated ones. When one major grain-producing region has a bad year, the others expand to compensate. What the system was never designed for is simultaneous stress across multiple producers at once. A strong El Nino can put Australia, India, and Brazil under drought pressure in overlapping windows, removing the surplus that normally absorbs a regional shortfall. And the countries most exposed to what happens next aren't the ones that grow the food. They're the ones that buy it. Across large parts of the Middle East, North Africa, and Sub-Saharan Africa, households already spend more than half their income on food in normal years. A sustained 70% price spike, comparable to the 2008 global food crisis, produces genuine emergency in those economies, and food riots broke out in more than 30 countries during that 2008 event. There is one more layer that wasn't present in 1877. The ocean is measurably warmer now than it was a century ago, not just at the surface, but through the upper 1,000 feet where El Nino dynamics operate. When an El Nino event develops in a warmer ocean, it starts from a higher thermal baseline. The same dynamics that produced a 3-degree anomaly in the pre-industrial Pacific now produce that anomaly on top of an ocean already carrying decades of accumulated heat. Whether this raises the frequency of events, the models haven't fully agreed on. But the intensity ceiling appears to be moving upward alongside global temperatures, and that means the events that were on the extreme end of what the historical record shows may no longer represent the upper limit of what the system can produce. Henry Blandford saw the pressure readings shift in April of 1877. He sent dispatches. nobody responded with the urgency the data demanded. By the time political leaders accepted what was happening, millions were already dead. The drought was the cause, the delay was the multiplier. Every monitoring system built since then, every buoy, every satellite pass, every climate model running on a supercomputer, was built to close that gap between signal and response. The Pacific has already sent its signal. What happens with it is the question the next several months will answer.